Good afternoon, ladies and gentlemen. Let's have a little discussion here about the formal definition of the derivative. We've been talking a lot this year about the derivative thus far, mostly with respect to the derivative informally. Informally, we know, or geometrically speaking, we know that the derivative is the slope of a tangent line to a curve. Slope of the tangent line to a function at some x value. We know that, and we've talked about that a lot thus far. What we have not discussed, and we are going to discuss, and it's important that we look at the formal definition. So, what we know so far is that given a particular function, arbitrary function in the purple there, that the derivative is defined to be the slope of this tangent line at some x value. So consider x of 1 right there. F prime of x of 1 is the slope of this tangent line at that particular x value. We can also say that, we've looked at this also with our calculator, and we've used this notation a lot thus far, this Leibniz notation, that dy dx at x equals x of 1 is the slope of the tangent line. What we're going to discover today, or find out today, is why that's true, and why that is true formally. And then we're going to use this formal definition of the derivative to calculate some analytical derivatives. Okay, so why is that formally? Well, let's go back in time a bit and look at some secant lines to a particular function. And again, I have this purple arbitrary function there, and I'm considering this secant line. The secant line is a line that passes through 2 points of a curve. This particular line goes to this point x, f of x, and goes to the point x plus h, f of x plus h. And notice what I've done here is x, I've gone over h distance. So the delta x, the change in x, is h. The change in y is f of x plus h minus f of x. This is the change in y. And this particular graphical representation will be important down the road also. So, the slope of this secant line would be the change in y's over the change in x's. X plus h minus x, which we know, x plus h minus x is just h. And if you recall from your pre-calculus days, this is the difference quotient in pre-calculus. Okay? So what I'm going to do now is give you another graphical representation and see what happens. So what happened? What's the difference between this picture and this representation? The only thing that's different is that this h value has gotten smaller. Still have the same points, x, f of x. I still have gone over this distance h to go to this x value, x plus h. So delta x, the change in x, is still h. The change in x is still h. I still have the same change in y, f of x plus h minus f of x. And I do have a clearly defined secant line. Well, what would happen if I take this h and go smaller? Well, I have an even a smaller h. Again, I have this point x, f of x, and this point x plus h, f of x plus h. The change in y is getting smaller too. You notice my h is getting small, but observe the tangent, the secant line, if you will. Look at that secant line. You can barely tell that it is a secant line. It doesn't look like it almost looks tangent. But does it? But this is still defined to be the slope of the secant line. So I've gone from large h, smaller h, and smaller h yet. smaller h yet. Well, what would happen if I continue to decrease this h? Well, that's what would happen. If I allow this h to go to 0, then I no longer have a secant line. I have a tangent line through the point x, f of x. And so when I notice that this is my difference quotient, this is the pre-calculus difference quotient. It's also the slope of a secant line. But as soon as I allow h to go to 0 and take the limit as h goes to 0, we can define that to be the slope of the tangent line. And this, ladies and gentlemen, is the formal definition of the derivative. So this is also f prime of x is equal to this limit formally. So we're going to look at this limit, a couple simple examples, evaluate that limit, and find some derivatives. Example number 1. Well, therefore, this is the formal definition of the derivative. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. Formal definition. Let us use this formal definition. Okay, so let's start with an example. And here's the example. F of x, 3x squared plus 7x. Now we have this particular course this year, the way we've approached it, is we've actually calculated analytical derivatives before we've kind of put the cart before the horse, if you will. Because we've calculated that, and we know that f prime of x is 6x plus 7 with respect to the power rule. So what we're going to do is we're going to show by using the definition, we're going to use the definition, the formal definition of the derivative, to show that the f prime, the derivative of that is indeed 6x plus 7. So I'm going to calculate this difference quotient. I'm going to take the limit as h goes to 0. And I'm going to see that f prime does equal that using this definition. So let's do it. The first thing I need to do is I need to calculate f of x plus h given this particular function. So f of x plus h is going to be 3. Keep in mind the function rule. The function rule is 3 something squared plus 7 something. And in this case, the something is going to be x plus h. There is a very nice video that accompanies this that's all about the pre-calculus version of this difference quotient. If you need to go back and review that video, please do. So, and this is the hard part, f of x plus h. It's not that hard, but I'm going to put x plus h in wherever I see x. So 3x plus h squared plus 7 times x plus h. This x plus h squared, recall from our Algebra 2 days, that x plus h squared is certainly the quantity x plus h times the x plus h, which by the distributive property is x squared plus 2xh plus h squared. That is what x plus h squared is. So I have 3 times that, plus 7 times x plus h, 7 times x, 7 times h. So this, and then I'm going to multiply through by the 3. 3 times x squared, 3 times 2xh, 6xh, 3 times h squared, plus 7x plus 7h. This is f of x plus h. If you need to pause the video, please do. And what am I going to do now? I'm going to put that into the difference quotient. I'm going to put this f of x plus h into the difference quotient, and I'm going to subtract from it f of x. I'm going to divide by h. Here we go. So this guy right here is f of x plus h. This is f of x. We need big parentheses here because I'm going to subtract f of x. If you don't put the parentheses here, this guy is going to end up positive and you're going to make an error. And we don't like errors. So, if I do some chalkboard math here, what's going to happen here? I'm going to distribute the negative sign, and this is going to be 3x squared minus 7x. And I'm going to simplify the top now, simplify the numerator. And notice, everything, and this happens every time with this difference quotient, everything without an h is going to subtract away. It's not magic, it's math. So I have 3x squared minus 3x squared. They're gone. They're gone. Let's cross them all. I have 6xh still there. 3h squared still there. Hey, what happens to the 7x? I have 7x minus 7x. They're gone. And I still have the 7h. So this is my difference quotient. 6xh plus 3h squared plus 7h over h. And I notice that every term on top has an h. So I can factor that h out of that top. And now this h will cancel. It's not magic, it's math. So the difference quotient then is 6x plus 3h plus 7. And what I'm going to do is I'm going to put that now into the formal definition of the derivative for that particular function. Here we go. So f prime for that function is the limit as h goes to 0 of 6x plus 3h plus 7, which is a very easy limit to evaluate. H goes to 0. Rule number 1 for evaluating limits, use substitution. Put 0 in for h. Bam, 3 times 0 is 0. What do you have? 6x plus 7. And bam, that's exactly what we thought, that's exactly what we said that f prime was, 6x plus 7. And I'd like to make a note about this particular. All of this here, all of the messy stuff, this is all pre-calculus topics. This is all pre-calculus. This is all not calculus. The calculus is knowing the definition. The calculus is knowing the definition and then evaluating this simple limit. So the two calculus steps are very simple. F prime, 6x plus 7, just like we suspected. Just like we knew. Let's do one more example. Example 2, f of x, x squared plus 3x minus 2, which we know by the power rule, the derivative is 2x plus 3. So this is where I want to end up when I use my definition. The limit as h goes to 0 of f of x plus h minus f of x over h. And what is the hard part? The hard part is evaluating, is simplifying this f of x plus h. So here's my function, and what am I going to do? Wherever I see x, I'm going to put in x plus h. So I have x plus h squared plus 3 times x plus h minus 2. And I'm going to simplify this f of x plus h. And I know that x plus h squared is x squared plus 2xh plus h squared. 3 times x plus h is 3x plus 3h minus 2. This guy right here is the f of x plus h, if you will. And I'm going to use a big parentheses. This dude right here is f of x minus all of f of x. Do some chalkboard math here. Distribute the negative sign up here. Negative x squared. Negative 3x. And negative makes that plus 2. And now I'm going to simplify this numerator. Everything without an h subtracts away. Okay, so what do I have? Let's scoot it up here so you can see it good. Okay, looks like I have an x squared. Oh, minus x squared. They're gone. I have, well, I'm going to drop that 2xh. Drop that h squared. 3x minus 3x. they're gone. Drop the 3h, negative 2 plus 2, they're gone. So this is the difference quotient. And what do I notice about all the terms in the numerator? All the terms have an h. Factor the h out. You can factor the h out so you can cancel the h on the bottom. Happens every time. Not math, not magic, but math. Factor the h out, cancel the h. So this 2x plus h plus 3, this is the difference quotient for that particular function. This is the f of x plus h minus f of x over h. 2x plus h plus 3. That's the difference quotient. I put the difference quotient into the definition of the derivative. F prime is the limit as h goes to 0 of 2x plus h plus 3. An easy limit to evaluate. Put 0 in for h. Bam. 2x plus 3, just like we knew. So, there are certainly harder versions of using the definition of the derivative, but we knew you need, as an AP student, to understand this definition, the graphical representation of this definition. This is important that you understand this, and important that you need to be able to use that for some simple functions. Nothing elaborate, but for some simple functions we need to be able to use that. Keep in mind, where did this come from? It's the limit of a secant line as this h, as the delta x goes to 0. Bam! The h's are getting smaller and smaller and smaller, hence the definition of the derivative. Okay. Thank you very much. See you soon.